Hello, everyone. Thank you for coming to my talk. I'll be your presenter for the day. And it is worth mentioning that this work was performed or accomplished with the help of my colleague Pankaj Sahad and my advisor, Dr. Madhusudan. The title of the work is PMK, and it's essentially a framework for analyzing a policy-driven multi-tenant Kubernetes environment. Without further ado, I'd like to start talking about some of the basis of our research. And essentially, we explore the notion of fairness in particular as we develop. So with that said, I'd like to start by asking a basic question is, what is fair sharing? And essentially, I'd like to set up the problem by saying that the goal of fair sharing is to have a number of users, or in this case, it could be tenants or communities actually sharing a common resource. I have as an illustration, I have in the right side of the slide, I have a CPU for the y-axis, and then I have the tenants stack up on top of one of another, on top of each other. And essentially we're giving tenant 1, tenant 2, and tenant 3 equal shares or equal division for this particular scenario. So in other words, the most basic way to share resources among people or among users or among tenants or among schedulers is simply to provide 1/n of the resource that's available. In this case, 1/n would be for the 3 users, and the n would be essentially the 3 users. We have 1 CPU, and then we want to share it among 3 users. With that said, our goal is, again, we want to share it through 1/n. Now, this is great and all. However, if we would like to further improve the way we share our ecosystem, we'd have to try to be a little more clever about it. And someone came up with maximum fairness, in which case became a generalization of the basic problem. And now with that generalization, we can have a user that will want less of the resources, less of what we think of equal share. In this particular case scenario, tenant 1 actually only wants 10%, and therefore we provide 10% of 1 CPU to tenant 1. So again, the solution is enables users to have less than their fair share. And for instance, I mentioned that tenant 1 or user 1 actually only gets 10%. Now, that same concept, maximum fairness, was also further generalized by using weights. And essentially, you assign a weight or priority to the particular tenant or the individual tenant. And then based on that, each tenant would actually be able to perform according or acquire the resources according to the weight that they have been assigned. Now that we have that, there is a pivotal question that we must ask is, why is maximum important? Again, we may have thought that it is a little important, but this type of algorithm is widely used. Essentially, it provides 2 desirable properties. And the desirable properties, first, isolation policy, that users get a fair share respective of the demands of other users. So it doesn't matter what other users want, you get a fair share that is available to you according to the particular region. So it's isolation guarantee. Then there is flexibility. It separates mechanisms from policy. And a few examples of that is proportional share and priority. Again, flexibility allows you to be able to work, for example, in the weighted max-min, we're able to actually assign priority based on the weights. Now, a few use cases for maximum fairness is that we use it in the OS for lottery scheduling. We use it in networking for weighted fair queuing, and we used to do it for data centers. A quick example of this is Hadoop Fair Scheduler and Hadoop Capacity Scheduler, which are essentially used very heavily in data centers. Now, with that said, now it is good to introduce that we only are talking about 1 single resource. So now that is a hint for this particular question, where we want to say, why is maximum not sufficient for data centers? And the short answer, you may figure by now, is that workloads consume more than just CPUs. And essentially, we are working with multiple resources, and we would have to do something a little more clever to make sure we factor in also the other resources in the midst. And you will already by now start to figure out that another generalization came about, which was called DRF, and it was actually essentially a generalization for multiple resources. DRF, again, stands for dominant resource fairness, and I'll be able to explain it a little more as we move forward. Now I'll try to introduce the basis of the problem and essentially some of the contributions we're going to make in this paper. As Kubernetes matures, with increased stability and scalability, it is important to continue to study how it can be effectively customized for use in different application scenarios. The focus of this particular framework is to study one of the Kubernetes main core components, which is Kubescheduler, which is in charge of scheduling paths on worker nodes. Essentially, we are trying to inform the communities so system administrators are able to make better and more informed decisions. Throughout the presentation, I'm going to be referring to individual tenants, and individual tenants essentially could be defined as a community, could be defined as a tenant of a schedule, could be defined as a scheduler or a framework. And essentially, those communities could be, you can think of those communities as a physics community or chemistry community or simply the computer science community. And you want to find out how can you share resources among these tenants, these communities, to be able to allow them to optimally launch their workloads into the cloud or into their particular infrastructure. So now that we understand sort of the scope of our contributions and some of our problem case scenario, it is worth also highlighting that the default Kubernetes off-the-shelf Kubernetes only implements first come first serve. We were able to learn that as we move through the research. However, it's worth mentioning right now that we did learn a lot, and we wanted to understand whether or not we can actually change or essentially cheat the system to be able to schedule the workloads a little more optimally using the different policies that we have. Now that we understand that, I'll introduce some of the motivation. So the main motivation is that we want to understand of the shelf Kubernetes scheduler architecture. And another motivation was that we want to continue to improve scheduling in Kubernetes multi-tenant environments. So essentially, we want to be able to provide those results that will essentially get back to the different system administrators or system admins to make sure that they are actually able to make informed decisions. So our goal for the entire research is to analyze and evaluate policy-driven environment for tenants with individual homogeneous demand, heterogeneous demand, and evaluation of fairness. So now I'd like to go over Kubernetes. I'll be going over Kubernetes very briefly. We are a little bit limited on time, but I'll be able to cover some of what Kubernetes is. So technically, Kubernetes could be divided into two major components, and the major components are control plane and compute nodes. In the control plane, however, is where most of the system is actually controlled. The compute nodes are essentially where your workloads are running. Any application you submit would be effectively executed in the compute nodes. Now, in terms of a control plane, we have 4 components in the control plane, which is Q API server. This is the way we access the API for Kubernetes, essentially the way we orchestrate or build the particular framework that I have built today. We have Kubescheduler, which also the Kubescheduler essentially is in charge of selecting the nodes where the tasks are going to be scheduled onto. Kube controller, essentially we can manage, there are many types of controller. An example of a controller in a Kubernetes environment is that no controller is responsible for noticing and responding when nodes go down. And then we have the ETC, which is a consistent and highly availability key value pair used to store all the data for the Kubernetes setup. Now that you have understand that, again, the item that we want to be making emphasis on in this is the Kubescheduler. And essentially, we do not make any changes to the Kubescheduler. However, in the next slide, I'm going to be able to show you how the scheduling pack context actually works. And then you'll be able to see where we actually place our particular framework that was implemented for this work. So here is a Kubernetes pod scheduling context. And essentially, the context is divided into two major parts. This is extensible API and internal API with scheduling cycle and binding cycle respectively. And essentially, we sit right on the top left corner where it says sort. We have P&K sitting right besides the start of the scheduling cycle. And we do not make any changes to the extensible API, which could be added or could be optimized or could be changed to the needs of a particular system admin. However, we do in there, we do try to, through P&K, we try to resequence tasks, and the way we resequence tasks is to see whether or not we can actually cheat the system. We did many trials for that, say. So now that we understand essentially where P&K would be, now it is worth talking about what P&K is and how it's composed. So for P&K, we actually created, divided into four small components, and one component is actually composed of two of them. So just to summarize again, P&K is a framework designed to analyze policy-driven performance in a multi-tenant Kubernetes environment. It helps cloud and cluster managers make informed decisions on how the task submission rates and scheduling policies can affect fairness in using the shared infrastructure for our tenants. And to better understand it, so for number one, we have that's where P&K client is placed. And this component is responsible for registering individual tenants, receiving new job requests, along with resource requirements, and submitting them to P&K for pre-processing. Then we have number two, which is P&K server. This component receives the task sent from the P&K client from each of the registered tenants. And then it would essentially spin up a worker for each of the tenants that are registered in the client and create queues respectively for that, whether it's one queue, a single queue, or individual queues for each of the tenants registered. And then we have two components that we have merged together into number three, which is P&K policy and workload queues. Through these two features, we enable tenants to pick the policy that would be used for scheduling. Both waiting and rating queues are synchronized with the queue scheduler. And finally, last but not least, we have the P&K scheduler. This component is in charge of dispatching the tasks, which are picked from the queues based on the chosen scheduling policy. Here is the way we actually have our setups. We have, as far as software, we set up our machines right from the scratch. So essentially, we install the operating system, Docker, and Kubernetes. In this particular case, we didn't necessarily add any other container solutions. However, that container solution is one of the main ones that we have. As far as hardware, we have CPU, we have homogeneous machines. In this case, we got actually 5 machines. We got 4 compute nodes and 1 for to use as a control plane or master node. Each node contains 48 cores and memory about 128 gigabytes of memory. Our policies that we study are round robin, which is the baseline for our research. Then we use first come, first serve, which is again also not necessarily a baseline, but one of the classical problems we wanted to include to see how the algorithms would perform. And then we have dominant resource fairness, which is a well-known algorithm at this point introduced 10 years ago by Gassi at Stanford University. Finally, we have CBF, and this is a variation of DRF that considers only resource availability instead of resource capacity. Again, I didn't mention, but dominant resource fairness takes into account a ratio of the most commonly used resource by individual users. Then it calculates based on the capacity ratio, and then the user that is actually utilizing, that has a dominant resource would not get that dominant resource right away. But in this particular case, we only consider what's available for the users that are actually needing resources for cluster-based fairness, CBF. This is the experimental setup, how we set up the demand vectors. Tenant 1 has 1 CPU, 1 GB of MEM. Tenant 2 has 2 CPUs, 2 GB of RAM, and Tenant 3 has 4 CPUs, 4 GBs of RAM for experiments 1 to 3. Now, for heterogeneous experiments, we actually decided, so we did a small random selection for each of the tasks. So therefore, for CPU, each task could range from 1 to 4 CPUs. And for memory, we can range from 1, 2, and 4 gigabytes of memory. As far as the way that they submit the submission rates for all the experiments, we try to create sort of the same format for both homogeneous and heterogeneous. In the homogeneous setup, we do 1 second for Tenant 1, 1 second for Tenant 2, and 1 second for Tenant 3. In other words, 1 second is equals fast submission, 1.5 seconds equals medium submission rate, and 2 seconds is a slow submission rate. Now that we understand the experimental setup, we understand the submission rates, we also understand the software stack and the hardware that we're going to be using. I like to start talking about the first experiment. So for all the experiments, before I start explaining some of what we see here, for all the experiments, I would be mentioning what we collect in terms of average waiting time, average turnaround time, and policy of fairness for observations, if it's applicable. It may not be applicable in the case that I may not have to mention it since there was not much extracted from the results. However, our goal for this first experiment is to understand how tenants perform under the same fast submission rate, but with different task resource requirements. We kept the submission rate the same to understand how Kubernetes internal decision-making mechanism performs with all different policies. If we notice, one thing that we notice right off the top is that right on the top corner, top right corner, we have round robin. Again, we see that Tenant 1 performs, has a make span that's substantially lower than the rest of the tenants, Tenant 2 and Tenant 3 respectively. On the bottom left, we have CBF, which is cluster-based fairness. And again, we have Tenant 1 actually take the lead in terms of resource make span and essentially resource utilization because he's hogging the cluster. Then on the right top corner, we have first come, first serve, again, which is one of the classical algorithms we introduced. And I mentioned it in the previous slides about when the problem was set up. And on the bottom tab, in the bottom corner, for the right side, we have DRF, dominant resource fairness. And again, we see it performs similar to round robin, CBF, and DRF. They all perform similarly. However, first come, first serve did not actually perform according to what we sort of expected. But essentially, we have to take into account that the users or tenants in this particular case scenario have different demand vectors. So therefore, perhaps the other one could have been visualized as fair, but if there was not necessarily improvement in the system, now we can think that it's unfair because the way the uses are distributed. So in the left figure that we have here in the presentation, we present how the average waiting time is consistently better for Tenant 1. Again, I mentioned that in the previous slide, compared to other tenants in the cluster. The results show that Tenant 3 received the worst allocation even for equal submission rate, which is again fast submission rate, 1 second. Our fairness observations for these experiments are the following. We observe that fairness is negatively affected due to the increase in the make span for individual tenants. Know that all the tenants receive the same fast submission rates. So again, we did expect something, but that's essentially, we can visualize that as not being fair to other users. And additionally, tenants have individual homogeneous demand vectors which influence the allocation cycle, this is what I explained, they are different. So therefore, it could hinder some of their performance. As far as experiment 2, we experienced similar items. However, we aim to understand how tenants perform under fast, medium, and slow, fast, medium, and slow for Tenant 1, Tenant 2, and Tenant 3 respectively. And essentially, we wanted to see if assigning like fast, how it would perform. We essentially kind of visualized or thought about how what we expected, but we wanted to understand essentially how it would perform, because essentially we're trying to improve Kubernetes, not necessarily our framework per se. So in our results, we learned that still around the tenant one was able to has the fastest submission rate and it aligns with Kubernetes default settings. Scheduling policies when each tenant is subject to PMK just resequence shows that in comparison to round robin, we actually perform according to the Kubernetes standard. So in this case, we are now, although the make span of tenant one is a standard in first come first serve on the top right corner, we're still able to perform fairly well or fairly or fair in comparison based on what we spent. Here in this particular experiment, for average waiting time, we expect tenant 3 to be disproportionately penalized for crucial attributes, a slow submission rate, and a slash homogeneous demand vector. So again, it's sort of like me seem like an obvious scenario. We wanted to see how Kubernetes would perform under these particular case scenarios, since we didn't understand the underlying infrastructure right off the bat. As far as CBF, scheduling policy, contain cluster-based fairness, we have for the submission rates improve both average waiting time and average turnaround time. Tenant 1 has the fastest submission rate and aligns with Kubernetes. Again, so similar type of what I actually have briefed you on already, but essentially worth highlighting. Now that you have I have covered 2 of the experiments for homogeneous, the next experiment was essentially not necessarily any different than what we actually see here. We do see a little better performance in terms of for first come first serve gets apply. It's something in terms of the way it makes span or how much resources each user takes. We're able to see it because now tenant 3 would have to become the fastest submission rate. However, that tenant 3 has the largest demand vectors as well. So we'd have to accommodate that effectively for Kubernetes to be able to process it. And a fact worth mentioning about Kubernetes is that it essentially takes the timestamp for which each task was submitted on. So when the task is submitted, that's the timestamp that it takes to be able to allow that particular task to be submitted to the cluster. Now, as for heterogeneous, we didn't see much of a change. Again, this is a fast submission rate. However, for all the other submission rates, resequencing, we were able to obtain very similar results as to the one that you see here. So in our case here, our policy and fairness observation is that resequencing on top of Kubernetes for mixed workloads presents limited opportunity for improvement. And this is essentially what we see here. We use round robin as a baseline and essentially outperform every single one of the policies ahead of it. Finally, I would like to highlight some of the items that are that we kind of discuss in this presentation, and then I will be talking about the future of the work. So for homogeneous demand vectors experiments, for all task submission rates, as expected, tenants with lowest individual demands perform better in terms of average waiting time than tenants with the largest demand vector. Tenants with the largest resource demand vectors are penalizing a constrained resource environment irrespective of fast submission rate for both average waiting time and average turnaround time. As far as for heterogeneous demand vectors experiments or mixed workloads with the same submission rate, CBF provided favorable fairness characteristics for at least one of the tenants. And finally, our experiment shows that this mechanism gives cluster and cloud infrastructure managers the ability to influence tenant average waiting time and average turnaround time. Essentially, I believe that we should expand the research and extend the research into exploring the Kubernetes kube scheduler for to improve the Kubernetes scheduling cycle, and by using that extensible tool to improve it, we can essentially improve the way we schedule tasks fairly. One more suggestion for future work is that we should try to include more emerging container solutions. In this case, Pacman. Pacman is very comparable to Docker. In fact, it has said very similar commands are used, and therefore it may be a seamless solution since it can be a rootless container solution. However, you cannot run it in the root context or the names on the kernel space as well. We also should try, instead of studying synthetic workloads, which is the one that we actually perform in our particular work, we should try to store more industry-based real work trace loads. In this case, we have Google, Azure, and Alibaba has been proven to be very good models of data for the cloud. And as far as for scheduling goes, Kubernetes is actually having built-in modules for Kubernetes, which they namely call feature gates. I believe that studying DRF variations with custom weighted given to each of the resource to decide dominant share is also very important. Feature gates are becoming a very core component of Kubernetes, since that's how most of the features outside of the basic container, basic Kubernetes setup this is the best way to introduce some of the pluggable features for Kubernetes. Again, this is something I would like to explore in the future. I believe that the fairness that we have explored has sort of reached a level that now we have to keep standing, and maybe not only standing, but studying and implementing, doing new implementations on top of Kubernetes and inside Kubernetes itself, to make sure that we are able to improve the way we schedule our tasks. Thank you for coming to the talk. I appreciate it. If you have any questions, please don't be afraid to send me an email. My email is abeltre1@binghamton.edu. Thank you.